In this lecture, I'm going to discuss how to linearize the function of two independent variables. Let f of x comma y be a function of two independent variables x and y. If the point is moving from x naught comma y naught to any other point, let us say x comma y, in the increments delta x is equal to x minus x naught and delta y is equal to y minus y naught. So take a point in the plane. This is the point x naught comma y naught. So take just x naught comma y naught is moving to the point, let us say x comma y. X is varying from x naught to x naught x by the increment delta x, where delta x is equal to x minus x naught, and y is varying from y naught to y naught with the increment delta y is equal to y minus y naught. So now by the definition of differentiability, f of x comma y minus f of x naught comma y naught, so that is equal to fx or the point x naught comma y naught into delta x plus fy at the point x naught comma y naught into delta y plus epsilon 1 into delta x plus epsilon 2 into delta y, where epsilon 1 and epsilon 2 tends to 0 as delta x and delta y tends to 0. Since delta x and delta y is very small, when delta x and delta y approaches to 0, then epsilon 1 and epsilon 2 approaches to 0. Since delta x and delta y are very small, epsilon 1 and epsilon 2 become 0. So therefore, f of x comma y minus f of x naught comma y naught is equal to, so dou f by dou x at the point x naught comma y naught into delta x plus fy at the point x naught comma y naught into delta y, you can write. So this can be written as f of x comma y is approximately equal to f of x naught comma y naught plus fx at the point x naught comma y naught, where delta x is x minus x naught plus fy at the point x naught comma y naught, where delta y is y minus y naught. So this implies, let us call f of x comma y, that is equal to L of x comma y. So where L of x comma y is called the standard linear approximation. Approximation of f at the point x naught comma y naught, where L of x comma y is equal to f of x naught comma y naught plus fx at the point x naught comma y naught into x minus x naught plus fy at the point x naught comma y naught into y minus y naught. So this is the linear approximation to the function f at the point x naught y naught, where fx is equal to dou f by dou x and fy is equal to dou f by dou y. Partial derivative of with respect to x and partial derivative of y with respect to partial derivative of with respect to y. Find the linearization of the function f is equal to x square minus xy plus y square by 2 plus 3 at the point 3 comma 2. Let us move to solution. We have linear approximation of the function f at the point x naught comma y naught, that is L of x comma y is equal to f of x naught comma y naught plus fx at the point x naught comma y naught into x minus x naught plus fy at the point x naught comma y naught into y minus y naught. Here x naught comma y naught is equal to 3 comma 2. Therefore L of x comma y can be written as f of 3 comma 2 plus fx at the point 3 comma 2 x minus 3 where x naught is 3 plus fy at the point 3 comma 2 y minus 2. That is equation 1. So let us find out f of 3 comma 2. The given function is at x comma y is equal to 3 comma 2. So f of 3 comma 2 is equal to, so 3 square 9 minus 3 into 2 6 plus y is 2 4 by 2, that is 2 plus 3 5, so that is equal to 8 here. So 5 plus 9 14 14 minus 6, that is 8. So now let us find out fx dou f by dou x at the point 3 comma 2. So let us find out fx, differentiate function f with respect to x partially, x square differentiation 2x minus y into x differentiation 1. So fx at the point 3 comma 2, so that is equal to 2 into 3 minus 2, so that is 6 minus 2 is 4. Find out fy, differentiate f partially with respect to y. So we'll get minus x y differentiation 1 plus y square differentiation 2y, 2 to get cancelled, that is y. So fy at the point 3 comma 2, so where x is 3 minus 3 plus 2, so that is equal to minus 1. So therefore L of x comma y can be written as f of 3 comma 2 is 8 here, 8 plus fx at the point p naught is 4, 4 times of x minus x naught where x naught is 3 plus minus 1 where fy is minus 1, fy into y minus y naught, y minus 2. So this is equal to 8 plus 4x minus 12 minus y plus 2. So this is equal to 4x minus y. So 8 plus 2 10 minus 12 minus 2. So this is the linearization of the function f, where f is equal to here x square minus xy plus y square by 2 plus 3. At this point we can linearize the function, so that is 4x minus y minus 2. Similarly, we can define the linear approximation to the function of three independent variable. So the linearization of function of three independent variable f of x comma y comma z at the point p naught x naught comma y naught comma z naught is defined by L of x comma y comma z is equal to f of x naught comma y naught comma z naught plus fx at the point p naught into x minus x naught, where p naught is x naught comma y naught comma z naught, plus fy of the at the point p naught into y minus y naught plus fz at the point p naught into z minus z naught. So is called the linearization of the function f is a function of three independent variables. Now let us define the total differential of the function of two variable. Let f of x comma y be a function of two independent variables x and y, and be a differentiable function and be a differentiable function, and its partial derivatives are fx at the point x naught comma y naught and fy at the point x naught comma y naught exist. Partial derivatives are existing at the point x naught y naught. So then the change of f is defined by delta f is equal to f of x naught plus delta x comma y naught plus delta y minus f of x naught comma y naught. Change in x and y, there is a change in f also, that is f of x naught plus delta x comma y naught plus delta y minus f of x naught comma y naught. So this can be written as fx at the point x naught comma y naught into delta x plus fy at the point x naught comma y naught into delta y. So this is from the definition of differentiability. So this implies df can be written as fx at the point x naught comma y naught into dx plus fy at the point x naught comma y naught into dy. This is the definition of total differentiable when f is a function of two independent variables x and y, where df is called absolute change in f. So df by f at the point x naught comma y naught is called the relative change in f, and df by f at the point x naught comma y naught into 100 is called the percentage change in the function f, or df is called absolute error in f. df by f is also called as relative error in f. df by f into 100 is called as the percentage error in the function f. Estimating the change in volume. So let us move to the problem corresponding the estimation of change in volume. Suppose that the cylindrical can is designed to have a radius of 1 inch and height of 5 inch, but that the radius and height are off by the amounts. It is incremented by the 0.03 in radius of the can, and decremented by minus zero point 0.1, okay, decremented by the zero point 0.1 inches of the height. Estimate the resulting absolute change in the volume of the can. You can see the change in volume. This is a corresponding changing in the radius and changing in the height of the can. So let us move to solution. We have volume of the cylindrical can, V is equal to pi r square h. So where r is the radius of the can and h is the height of the cylindrical can. Okay. Now, if you want to changes in the volume of the can, so that is dV can be written as, so changes in volume of the can be seen changes in the radius r and radius h. So by using the concept of total differential, we can write, so that is Vr dou V by dou r at the point r naught comma h naught into dr Vh dou V by dou h. Changes in height of the can, we can see the changes in the volume of the can also. Dou V by dou h at the point r naught comma h naught into dh. So by using the definition of total differential, I written. So here r naught comma h naught, radius of the can and height of the can initially, that is 1 comma 5. So let us find out dou V by dou r. Let us call equation, this is 1. Differentiate V with respect to r partially. So Vr is equal to, so r square differentiation 2r 2 pi rh. So Vr at the point 1 comma 5, so is equal to 2 into pi, where r is 1 year and h is 5, so 10 pi. So now differentiate with respect to h, that is Vh, so pi r square. Vh at the point r naught comma h naught, that is 1 comma 5, that is equal to pi into, where r is 1 square, that is equal to pi. And here dr is equal to, that is equal to 0.03, and dh is equal to, so minus 0.1, minus 0.1. So therefore change in the volume of the can, so that is dV, can be written as, where VR at R0, H0 is 10 pi into dr is 0.03 plus VH at the point 1, 5 is pi into dH is minus 0.1. So this is equal to, after simplification, we have 0.63 inch cube. Therefore change in volume of the can is equal to 0.63 inch cube when there is a change in radius of the can and change in the height of the can. We can find out the relative change in the volume of the can. So that is dV by V. So where dV is equal to here 0.63 inch cube, otherwise you can write in terms of pi, 0.2 pi by, where V is equal to pi r square h, pi r square h. So here this can be written as 0.2 by pi get cancel, r square into h. So this can be written as 0.2 by r naught square into h naught. 0.2, where r naught is initially, that is 1 square into 5. So that is equal to 0.2 by 5. So that can be written as 0.04. The relative change into 100, dV by V into 100, is the percentage change in the volume of the can. So that is equal to 0.04 into 100. So 0.04 is the relative change in the volume of the can. So into 100, so that is equal to 4. Therefore 4% as an estimate of percentage change in the volume of the can.